computer. All right. One lecture where time is of the utmost importance, I'm wasting time. Anyways, all right. So when we're looking at the kinetics of the problem, and the problem is asking you to, the problem is completely described for one position, and it asks you to find out things that are happening in another position, immediately work energy principle. Or if you have a decent professor like me, who's going to tell you problem 3 on the exam is going to be work energy principle, all right? But in general, when you're applying and you're looking into these problems, what you have to see is that when you are the problem, the motion is completely described in one position, and you're asked to find out what's happening in another position, that's when you have to use the work energy principle, right? So here, you've got a 4-kilogram rod AB, which is attached to a collar of negligible mass, and it's frictionless. This moves up and down. We're assuming that, even though the problem doesn't say that. And you're told that the flywheel has a mass of 16 kilograms and a radius of gyration of 180 millimeters. That basically means that um, the rotational moment of inertia of the flywheel is equal to, it's just mk squared, where that's just the mass times the radius of gyration. That's just the definition of radius of gyration. So you're told that in this position that's shown, the angular velocity of the flywheel is 60 RPM clockwise. So it's 60 RPM like that. And you asked to find out the velocity of the flywheel when this point is directly below here. All right. So what's happening in this question is that you're given this position. So let's just say that this is position 1. And here, the motion is completely described, right? Because we know about the point, the point B is joined, we can use the kinematics to find out exactly what's happening with the rod AB, right? And that will help us to find out the energy of the system in this position. And then our second position is basically, all right, this is where Ashish Picasso comes into the picture. Terrible. So let's see. That. Let's see. This is the collar is at its lowest position. And you've got like that. Told that the rod AB goes to that position like that. All right. So here, now what I've got is I've got the point C right there. I've got the point B right there. And point A is right there. And this is the position in which the problem is asking me to find what the velocity of the flywheel is going to be at that point. Right. And remember, the one thing to remember here is that when I'm looking at the rod, right, you always want to know for your rigid bodies where the mass center is, because that's where the potential energy is going to go, and that's where you're going to apply and find out your Ig omega squared term, right? That's the kinetic energy. So here, G is going to be in the center, and here as well, G is going to be somewhere in the center. Those are all of the things that we are going to figure out. All right. So in this position, everything is described, right? So all I'm going to do in this problem is I'm going to equate my kinetic energy at position 1 plus my potential energy at position 1. And where's the best place to choose the datum for the potential energy?
Is it below?
What do you think is the best position? Below, you mean somewhere here?
No. Yeah, if you're looking at the first drawing, yes.
I think the easiest place, and you guys can prove me wrong, is to have the datum be right there, because then you don't need to worry about the potential energy of the flywheel. You only need to worry about the potential energy of the rod, right? So if I can have my datum be there at those two positions, and then all I'm concerned with the kinetic energy is that height y1 and that height y2. All right, and I can say that about this point here, my potential energy for both these positions here, it's just going to equal mg y1, and it's positive because it's above the datum, and here it's just going to equal mg y2. All right, now for both these positions, let's write out what the kinetic energy is going to look like, right? By the way, does that make sense for the potential energy?
Makes sense, but I do have a quick question.
Yep.
So we pick G at the center of AB. Is that just because AB segment or that rod is the only thing that's actually like moving or changing?
No. You have two rigid bodies here, right? You have your disc or your whatever this is called, flywheel, right? I really wish I got into race car more. But all right, there you go. That's your flywheel. That center of mass is right there. And then you're having your rod, and that's the G force. You've got to look at the two rigid bodies and those two mass centers separately. Here, it's just in the halfway point, right? So if this is 720 millimeters, what I mean by that is that that distance there is going to equal 360 millimeters. All right, so now if we write out, all right, are you guys with me? There's going to be a lot of things that happen in this problem. So just stop me and ask a lot of questions. So now we write the kinetic energy of the system. Let's look at the rod AB first. So the rod AB is both rotating and translating, right? So we've got to use our general plane motion expression. So that's just the mass of the rod AB times whatever the velocity of the mass center is, Vg squared, plus half times Ig times whatever the angular speed of the rod is squared. Right? So this is your kinetic energy for the rod, right? And it applies in both positions. All right. Then you also have the term due to the pure rotation of the flywheel. So this one, for the flywheel, you don't need to worry about translation because there's no translation that's happening off the mass center. So that's where the mass center comes into the picture, Mr. Simpson, again. So here, all you have to worry about is IC of the disk of the flywheel and omega BC squared. So these three terms completely describe the kinetic energy of your system. And this term here completely describes the potential energy of the system, right? So the trick now is to get, so remember, when we are doing energy, when we're equating energy at position 1 to position 2, how many expressions do we get? It's a scalar quantity. So how many equations does this expression give us? This, I'm pointing with my finger. Does this expression give us? T1 plus V1 is equal to T2 plus V2.
3?
No. This is a scalar quantities in here. It's only going to give you one expression. All right. So the trick here is that in position 1, we have to find out what Vg is and what omega AB is, and omega BC is given to us in this problem. So we are going to find out what Vg is and what omega AB is from the completely described motion of the flywheel. And in position 2, we're going to treat omega BC as an unknown and find out Vg and omega AB in terms of omega BC. And that ways, we only have one unknown that is going to go into this expression to find out what omega BC is in position 2. And how do we equate those velocities? Kinematics. Come on. It's the same thing. We've been talking about this. All right. So, are you guys with me? Questions?
So just to recap, so we're counting both center of masses for the AB rod and the disc, both for their translation and angular momentum. But since the disc is stationary,
angular momentum, angular kinetic energy.
Angular kinetic energy.
Yep.
And we can disregard translation for the disc because it's just stationary. It's not
absolutely
moving.
Yeah. Okay. Mr. Strout, you had a question?
So
You just find the center of each like individual object.
Exactly.
All right, so it's like sectioning.
Superposition. Yeah.
Okay.
All right. And now all of these expressions that I'm writing, they're valid in both these positions, right? So we're going to find out the general terms and then look at the two different positions. It's easy, but again, tedious. All right. So from kinematics, right? What can I relate about these two rigid bodies? The point B, right? So when I'm looking at my flywheel BC, I can say that the velocity of point B is equal to, again, I put my frame of reference at the point C, right? VC is equal to 0. Velocity of B with respect to C is 0. That doesn't change. That distance doesn't change. So I only have the term omega BC. How are you guys feeling about rigid body kinematics, by the way?
Interesting.
Confident or need more practice?
could
Definitely
always
a
use
little
more
bit more practice.
Okay.
Yeah.
Does this expression make sense, right? So this expression comes from the fact that it would be, I'm putting my frame of reference at there. It would be VC plus V of B relative to C plus this term here, right? That's just 0 because it's fixed, and that's just 0, right? Because B is not going to be extending in relation to C, right? So this is my expression for VB. Again, remember, the motion of the flywheel is completely described. All right, and then when I look at my rod AB, I move my frame of reference to the point A, right? So my VB is just equal to VA, and now VA I know is not going to be equal to 0, right? VA is moving up and down in the J hat direction. The collar is sliding up and down. Plus, I have V of B relative to A. Again, the length of the rod is fixed. It does not change. So this term is equal to 0. Plus omega AB crossed with R of B relative to A. All right, and this is my second expression. And that's it. All I have to do at the two different positions is find out what VA is. Let's treat that as an unknown. So in the Mathematica notebook, I call it U. And I know that VA is moving up and down. So it's in the J hat direction. So U, J hat, meters per second squared. That's one unknown. And my second unknown is omega AB, which is just equal to omega K hat radians per second. So if I solve for 1 equals to 2 to find out what VA and omega AB are going to be. Why do I care about what VA and omega AB are? Because in order to find out what VG is, I need to find out those things, right? And the only way to do that is to look at the kinematics of this point over here. So now when I do 1 equals to 2, and I find out what my VA and my omega AB are, I can say, when I'm looking at the rod AB again, that my VG is just equal to VA plus omega AB crossed with R of G this time relative to A. And this is my third expression. From here, I'll find out what VG is. Everything is completely described in position 1. So I'll get one term. In position 2, I will just find everything out. I will treat omega BC as an unknown, find out U and omega in terms of omega BC, and then find out what VG is again, plug everything back into this master equation, and that's it. That's the overall way to solve the problem. Now we just have to figure these things out. Is that clear, guys?
It makes enough sense.
We want to be making dollars, not cents anymore. All right. All right. So to find out the stuff that we can just get out of the way, so IG is just equal to 1/12 times MAB times LAB squared, right? And I plug it in. I know my mass of AB is equal to 4 kilograms, and I know the length is equal to 720 millimeters. Convert that into meters, please. And I find out that my IG turns out to be equal to 0.1728 kilograms meter squared. Similarly, IC is just equal to MBC K squared, where that K was the radius of gyration, right? 180 millimeters. So that's just equal to, if I plug it in, convert everything, I get that that's equal to 0.5184 kilograms meter squared. All right. So now let's get into it. So I'm going to look at the two different positions. So what I'm going to do is I'm going to bring this guy. You know what? I'll just move on to the next page. Man, this is the thing about teaching using this. You don't have a massive whiteboard where you can just quickly go back and refer to stuff. But anyways, well, what can we do? All right. So this is my position 1, right? So at position 1, right, omega BC in the problem is said that it's 60 RPM. So convert that into radians per second always. So minus, and it's in the clockwise direction. So it's minus 60 K hat, right? So you get minus 60 times 2 pi over 60 times K hat radians per second. So you just get minus 2 pi K hat radians per second. So that gives you a proper number. Then remember, for doing 1 equals to 2, I have to find out what R of B relative to C is. And I also have to find out, all right, so just to make things clear, right? This is the things that I can find out. This is given to me in both positions. Sheesh, it's not given to you in position 2. We're going to treat it as a known so that we get these guys, U and omega, in terms of omega BC at position 2, right? And what we're just trying to find out is VA and omega AB. All right. And then we also have to find out what R of G relative to A is. All right. And plug this value in there. All right. So now R of B relative to C. So you're just going, oh, again, all right, guys, always forget to do this. Obviously, Y and X, right? So R of B relative to C is going in that direction. So it's just going to equal minus, converting the millimeters into meters, so minus 2.4 I hat meters, right? And then you have R of B relative to A, which you're trying to find, and that's just equal to, all right, so now I'm going to have to do, so this distance is equal to 720 squared minus 240 squared, right? And that comes out to be equal to 678.8 millimeters, right? So R of B relative to A is just equal to minus 2.4 I hat and minus 0.6788 J hat. All right, and that's it. We have everything we need to find out what omega AB and VA are in this position. So I'll post, the Mathematica notebook is already been posted online. So I'm just going to tell you guys what we get. So solve for equation 1 equals to 2, which is basically this expression for BC and this expression for AB, right? And you end up getting that at this particular position, omega AB is just equal to 0, and your VA is equal to 1.50796 J hat meters per second. All right, and then from expression 3, which is this expression here, I need to find out what VG is. I say that my VG is just equal to VA plus omega AB crossed with R of G relative to A. Joy omega AB is equal to 0. So I don't even need to find out what R of G relative to A is. So that whole term is equal to 0. So VG is just equal to 1.50796 hat. So what that means is that in this particular instant over here, AB is in pure translation. It's just moving up. All right, guys, we're going to go over today. And if you guys have to leave, that's okay. I'll post the recordings online. But we just want to get through with this so that you guys can do your last homework. All right. Okay. Apologies beforehand. All right. But are you with me so far? Does this make sense?
Yeah, I'm following.
Yes, we're here.
All right. Next, what we have to do is find out what this height over here is, y1, right? So, because that's where our datum is. So if we look at that like that, like that, like that. So that's the midpoint, right? So we know this big length here is 720, and this is 240. So this length here is going to be 360, and that length there is going to be 120. This is all millimeters, millimeters, millimeters. So this length here, y1, that's just going to equal the square root of 360 squared minus 120 squared. And that comes out to be equal to 339.41 millimeters. Or, because we want everything in meters, so 3391 meters. So now we're ready. Avengers assemble. So at, right, Avengers assemble, but how do you spell energy? I don't know. Energy at position 1, right? I'm going to write out my kinetic energy first, which is this term over here, and I'm directly just writing it out, right? So if just bear with me. So energy at position 1 is going to equal the kinetic energy, which is half times m for the rod, which is 4 times Vg squared for the rod, which we didn't have to convert this into a scalar because it's only one component, right? So you can just directly write that out. 1.50796 squared, right? Plus 1/2 times the Ig for this guy, which was 0.1728 times omega AB squared, which is just 0. So this term is just 0 squared. So that's this term just goes to 0. Plus 1/2 times IC, which is 0.5184 kilogram meter squared, times omega BC, 2 pi squared. Right? So this is T1, the sum of these 3 terms. Plus, you have your potential energy of the rod AB due to Y1. So that just comes out to be equal to mg Y1, right? So that's just 4 times 9.81 times 0.33941 meters. All right? This term here, whoa, what a terrible bracket. This term here is equal to V1. All right. So here you'll get one number for your energy, for your left-hand side for your energy equilibrium. And that's it. You are done for that side. Next, we have to go in and do the same thing for position 2. Come on. So now at position 2, the first thing to do, omega BC is going to be your unknown, right? So we'll just write that out first so that we can find out everything else in terms of omega BC. So omega BC in the Mathematica notebook, I just call that omega 1, right? Because I'd already chosen omega for omega AB, right? So that's omega 1 k hat radians per second. For here, R of B relative to C is just, the radius of the disk in the negative j hat direction, right? So you get minus 0.24 j hat meters, right? Then you have to find out R of B relative to A. Again, that's the whole length there is 0.72 meters, right? So you're just going in the negative j hat direction, so minus 0.72 j hat meters. So now what we do is do the same thing, but we're solving for term to find out what VA and omega AB are in terms of omega 1. So solve for VA and omega AB in terms of omega 1. Now, for this problem, VA, you'll always, all right, never mind what I was going to say. Don't want to confuse you guys even more. By doing equation 1 equals to 2 by using the stuff that you have up here. All right, you do that, Mathematica tells you that at this particular instant, VA is equal to 0 and omega AB, so your rod is in pure rotation at this point, omega AB turns out to be equal to omega 1 over 3, and that's in k hat radians per second. All right, so omega AB is equal to omega BC over 3 in this particular instant. Then from my expression number 3, I see that VG is equal to VA plus omega AB crossed with R of G relative to A. Now this term here, VA, is equal to 0, right? So all I did this one by hand, but you guys don't have to. You can do it in Mathematica. So that's just going to equal omega 1 over 3 multiplied by minus 0.36. Oh, I didn't, right. Ashish, you're using shortcuts over here. So I need to find out R of G relative to A, right? So that's just minus 3.6 j hat, right? So that's minus 0.36 over here. And then for the actual cross product, this one is k hat, and then this one is j hat, right? K cross with j is equal to minus I, right? So you end up with minus gets canceled. So you get 0.36 over 3 omega 1 I hat radians per second. And this, guys, is just for completeness' sake. But in this particular problem, you don't need to worry about it so much because you're only concerned with the scalar quantity, right? So, yeah. All right. And then for your potential energy, I need to find out what Y2 is. And that is just equal to, so this height there is 0.36. So that's just equal to 0.36 minus CB, which is 0.24. So that's 0.12 meters. Right? So for my potential energy, I see that y2 is just equal to 0.12 meters, right? And that's it. I'm done. T1 plus V1 is equal to T2 plus V2, right? I'm going to rewrite it, right? So we'd written out T1 as being equal to 1/2 times 4 times 1.50796 squared plus 1/2 times 0.5184 times 2 pi squared, right? So this whole mess is equal to T1 plus my kinetic energy at that point, which did I find out mathematically? No, so it's just this thing. So in the notebook, I think I found this out mathematically. So this was 13.3185 joules. Yeah, 13.3185, right? This is V1, and that everything is known here, right? Just a matter of plugging it in. That is equal to my kinetic energy at position 2. So that's equal to 1/2 times 4 times now my VG is just this term over here, right? So it's 0.36 over 3 omega 1 squared plus 1/2 times 0.1728. So this is your IG omega AB squared term. This is for the angular rotation of your rod, right? So 1.1728 times omega 1 over 3. Remember, omega 1 is omega BC squared, right? Plus, now you have your I omega squared term, but for the flywheel, so 1/2 times, and the rotational moment of inertia there was 0.5184, and this one was just omega 1 squared, right? So this whole mess here is equal to T2. One second, guys, just want to make some more space. Plus your term for the potential energy, so that's 4.9.4 times 9.81 times 0.12. Remember, the datum was at the center of your flywheel, and this term here, oh, come on. This term here is equal to V2, and I think in the notebook I write out what the number is, so it's just 4.7088 joules. So remember, be careful of your units, keep everything consistent, it's just tedious. So now you have one expression for one unknown, omega 1, and that's it. So we solve. So we solve for omega 1, and that comes out to be equal to 8.86548 radians per second. Now remember, energy conservation, unlike kinematics, is dumb. You're just looking at what's happening in position 1, what's happening in position 2, finding out what the magnitudes are. So you don't really know what's happening with the direction. All you can do is assume. So what you can assume is that because initially it's moving clockwise, when it gets to position 2, it's also in all likelihood going to be moving clockwise, right? So you can say that omega BC is just equal to minus 8.86. I'm just simplifying this, 865 k hat radians per second, right? The minus comes in because we're assuming with all the information that we're given that this is going to be clockwise. All right, guys, how's that? Questions? Do you guys like camping? Because
Yeah.
it's also like dynamics. It's intense.
Not if you have a camper.
That's true. Then it's not. That's right. All right. Well, Mr. Franciscus, thank you. Yeah. All right. Does this make sense, guys? All right. Let's run through the process. Are you good with this page? I know Mr. Simpson didn't write down anything, but
No, I've developed a habit to just rewatch the recordings and write it
That's
out because
good.
I can't keep up with you.
That's good. All right. That's totally okay. Remember, work energy, problem 3, everything is going to be described in position 1. You're going to have to find out your unknown velocities, translational and omega, due to the completely described motion of one rigid body. In position 2, you will have to treat one of them as an unknown and find the rest. In terms of that, just do your work energy conservation, your energy conservation to find out what that one unknown is. And then look at the problem, make sense of what the direction might be, and report your final answer as a vector, always. Questions, guys? This is going to be problem 3. Remember, in your exam, you're going to have a problem like this. All right, and finally, I wanted to do a problem where we're looking at your linear momentum and angular momentum. Again, no exam problem, but you'll have one homework problem from the homework today that has to do, it's basically almost the same problem, but you have to use similar concepts. So you basically have a sphere of radius r and mass m is projected along a rough horizontal surface, right? So there's no slip here. There's like friction over here. And you're saying that if the final velocity of the sphere is to be 0, so basically it's not rotating or it's not translating, you're asked to find out what omega naught is in terms of v naught and your radius r. And you're also asked to find out the amount of time it's going to take for the sphere to come to rest in terms of v naught and the coefficient of kinetic friction, mu k. All right, first thing to do when you're having rotation is go to the back of the book and be like, yo, I don't know what the for a sphere, what the rotational moment of inertia is about its mass center. Go to the book, looking it up. It's 2/5 times mr squared. All right, and what we're going to do to solve this problem is we're going to look at the linear and angular momentum at position 1. We're going to look at the external impulse that is applied along the duration when this thing comes to a stop, right? So this is from position 1 to position 2. And then we're going to look at the final both linear and angular momentum at position 2. All right, so let's do it. So we have this there, we have this there, and we have this there. All right, so initially, what's happening is when you throw it onto the surface, right, you've just got your mv naught like that in the horizontal. So again, obviously, You guys should shout at me. Coordinate frame, yx always, right? So you have mv naught in the x direction, and you're also told that you're going to have an angular momentum. And let's just, as I told you guys, it's always just better to work about the mass center unless the problem might be easier to do otherwise. So we'll just say that it has an angular momentum of ig omega naught initially. All right. Then for all of the external forces that are acting on the body, what do we have? We're going to have the weight, right? So that's going to cause a linear impulse, right? We're going to have the normal force, right? So that's going to cause a linear impulse as well. And then when you're throwing this on there, right? You know, in general, you're moving in one direction. Your friction is going to oppose that motion. So your friction acts like that. So that's going to be the impulse due to your friction, right? And then at the end, what happens at the end?
Complete stop.
Everything's zero. So this is zero, and your angular momentum is also going to equal zero. All right. So now let's do linear momentum in the y direction, right? So from here, what's the linear momentum in the y direction?
0.
Zero. Right? What are the forces in the y direction?
The weight and normal force.
Right. So nt minus wt, like that. And what is your final momentum in the y? Zero. So this gives you your expression number one. Then you do linear momentum in the x direction, right? So here, what's your linear momentum in the x direction?
MV naught.
mv naught, right? Minus your frictional force, right? So minus ft like that. And what's your final momentum in the x direction?
0.
Also zero, right? Okay. Then finally, you'll get one more expression for your angular momentum, right? Let's treat the counterclockwise positive. What is your, and we'll do it about g. What is your initial angular momentum?
For IG omega naught.
Ig omega naught. What is your angular impulse about the point G? Remember, your angular impulse is the moment of the momentum, right? So here, you're going to have a moment due to this force F, and that's going to be R cross F, and then you have the time period T over there, right? And because it's going to be clockwise, it's going to be negative. So your angular impulse here is just FTR. Does that make sense, guys? If it doesn't
Wouldn't
make
be
sense, think
cross,
of it this
would it?
way. It's going to be minus FR, which is the moment, right? And then you convert that into an angular impulse, right? There's going to be no moments due to the weight and the normal force because they pass through, the lines of action pass through your point G. And you're looking at your angular momentum about G. Is that clear, guys?
Yep. But you're saying F cross R, right?
R, I believe it's R cross F, right? Yeah. All right, that is equal to zero. So you get three expressions. Now let's see how many unknowns we have. So we have normal force, that's an unknown. Obviously time, that's an unknown. We've got this frictional force, that's an unknown. And you've got, I guess, we've also got, we have to find everything in terms of V naught, R, and mu K, right? So, oh, and omega naught here, required magnitude. So omega naught is an unknown as well. Oh no, we have 3 expressions for 4 unknowns. Where do we get the last expression from?
All of this is linear momentum, right?
No, first 2 is linear, last one is angular.
Can we use conservation of energy?
No, right? Because you have external forces acting on the system. Friction basically is acting on your system. You could try to use work done, but there's a simpler equation to get, right? Remember, they're asking you to find terms in mu k, and you know that sliding is happening. So you can say that F is equal to mu k times your normal force, or mg like that. Or actually, you know what? You guys will be like, Ashish, that's not true. Yeah, you're right. So it's just mu k times n like that, right? And remember that your W is equal to mg. So this gives you your 4th expression. So you solve all of these and you see that omega naught is equal to 5/2 v naught over r, and you'll find that your time period t is equal to v naught over mu k times g for when it comes to a stop. Is that clear? All right, been a long and arduous journey. We're done with dynamics, at least from my point. So now it's up to you guys to study, do the homeworks, and do the exam next week. All right, so start studying from this weekend. I hate to have become the professor that gives the advice that I hated most from my professors, but start studying from this weekend. I will attend next weekend's LA sessions, which are going to be the last 2 LA sessions on Monday and Wednesday. You guys have questions with your last homework, with the problem set, practice, 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 and come and let's have a discussion and talk about things. All right, I will post this on Brightspace as well. On
So are
Tuesday,
you still,
yeah, go ahead, Mr. Franciscus.
are we still doing the in-person thing or no?
No, we're not doing the in-person thing.
Okay.
I'll because of COVID. So yeah, I'll tell you, it'd be a live Zoom lecture with me being awkward in the lab. So yeah.
Could you state again when the test was going to be available? I was in the other room.
Yeah, it's going to be posted on Friday night next week. And then you'll have Saturday, Sunday, Monday, Tuesday, and it'll be due Tuesday night.
All right.
Hey, Professor Ashish, if you got
Yes.
time, can we talk
Yes.
about number 5 and 3 from the homework?
Yes. Give me 1 second.